one of the most conspicuous and high-level physicists of our time, has offered his viewpoint on this issue. Michio Kaku, renowned for his remarkable contributions to the field of physics, recently confirmed that the James Webb Space Telescope has discovered 6 massive galaxies that scientists previously believed could not exist. These findings have the potential to open new dimensions in our scientific understanding of the universe. The discovery is both exciting and revolutionary, challenging existing theories about the formation and evolution of galaxies. Therefore, it is worth keeping an eye on these developments. The confirmation by such a distinguished scientist as Michio Kaku underscores the importance of these findings. Kaku is a prominent figure in the scientific field, a physicist of American and Japanese heritage, considered an expert in both classical experimental physics and quantum mechanics. Unlike some more conservative and skeptical scientists, Kaku is not part of that group and has been open to the groundbreaking results of the James Webb Space Telescope mission. His willingness to embrace new discoveries and share them with the public highlights his commitment to advancing our understanding of the universe. We are truly glad that this distinguished scientist has chosen to break his silence and publicly share what can no longer be denied. The excitement and almost amused tone of the renowned astrophysicist are evident in his comments about the discovery made by the James Webb Space Telescope. He expressed that this has been a highlight that has piqued his curiosity. Join us as we explore the implications of Michio Kaku's revelation of these 6 massive galaxies. Michio Kaku is a scientist who has always been willing to consider new theories. Throughout his life, he has demonstrated openness to ideas that challenge the status quo, understanding that Einstein's equations of relativity and Newton's laws, while fundamental, are insufficient to capture the full complexity of the universe. Kaku understands that the discovery of these new galaxies has the potential to enrich the scientific field. Although many of his colleagues have not been able to adopt this perspective, it is causing concern and insomnia among proponents of the Big Bang Theory and opponents of quantum mechanics. However, this only provokes laughter from Kaku. The James Webb Space Telescope has revealed the discovery of 6 enormous galaxies dating back to the earliest times of the universe. Each of these galaxies contains more stars than our own Milky Way, despite having formed just a short time after the Big Bang. The team of astronomers who made the discovery has named these extraordinary galaxies universe breakers because, if confirmed, they would change our entire understanding of the universe. The implications of these findings are profound, suggesting that the universe's early years were far more dynamic and complex than previously thought. Something no longer fits here. The Big Bang Theory tells us that the universe was a chaotic mess after the initial event. Solid objects took hundreds of millions of years to form, and it took millions more years for those objects to reach sufficient density and produce light. The formation of complex structures like galaxies was expected to occur much later. Some of the discovered galaxies surpass the Milky Way in size, and their immense brightness suggests that they were likely forming hundreds of new stars each year, whereas our galaxy forms stars only sporadically. It remains unclear exactly when the first galaxy formed. Scientists have not been able to determine this definitively. What is clear is that initially, there may have been only individual stars or clusters of stars, which eventually merged to form increasingly large conglomerates until dwarf galaxies developed. The small galaxies interacted with others and gradually grew. According to previous theories, highly organized and massive galaxies could not have existed at that time. This raises the question of whether the universe is much older than previously thought or whether complex cosmic structures developed much earlier. This scenario is difficult for conservative science to accept, as it still finds issues with this model. Some areas of physics heavily resist accepting this discovery and question possible errors in age calculations. Michio Kaku is aware of this and had this to say. There are many examples of old and false theories that stubbornly persist because of the prestige of certain scientists. Many of these theories were only discredited when a crucial experiment revealed their flaws. Thus, the essential work in any science, especially in physics, lies with the experimentalists who keep the theorists alert and awake. In reality, on Earth, we know almost nothing about the true origins of the universe. This statement from Kaku emphasizes the importance of continuous experimentation and validation in the scientific process. The Big Bang theory was established in 1927 based on observations of the expansion of the universe. These data led to the conclusion that the universe began from a single point and has been expanding ever since. At the time, it was difficult for people and scientists to conceive of a universe with a beginning and an end. The idea of a universe that had always existed and was infinite was beyond people's imagination. Even today, scientists still face difficulties in understanding it. However, it is essential to consider these possibilities. Nevertheless, these new revelations do not fit at all with what experts have long based their understanding of the Big Bang on. However, science has shown time and time again that reevaluation and openness to new ideas are a crucial part of the scientific process, as is the validation of certain theories and observations. When Einstein was young, it was believed that the stars and planets were firmly fixed in the universe, occupying a defined space. However, we now know that everything in the universe is in motion. Planets orbit stars, stars move within their galaxies at hundreds of kilometers per second, and entire galaxies move rapidly through the universe, the fate of which we cannot yet even predict. This dynamic understanding of the universe challenges long-held beliefs and underscores the need for continued inquiry and adaptation in scientific thought. Today, scientists face unprecedented challenges. These challenges arise not only from the complexities of the discoveries but also from the resistance to change within certain scientific circles. The new findings from the James Webb Space Telescope are forcing researchers to reconsider long-standing assumptions about the formation of the universe, and this process is often met with skepticism. However, history has shown that scientific progress thrives on such disruptions. When Copernicus first proposed the heliocentric model, it faced strong opposition, as did Darwin's theory of evolution. In each case, the prevailing paradigms of the time were eventually overturned by evidence too compelling to ignore. Michio Kaku's openness to these revolutionary findings highlights his understanding of this very principle, that science must remain flexible and ready to adapt as new data emerge. The discovery of the 6 colossal galaxies, potentially older than the Big Bang theory suggests possible, is not just a challenge to one theory but to the broader understanding of cosmology. The galaxy's sheer size, luminosity, and age imply that the early universe was far more organized and active than previously believed. This raises profound questions. Did the universe evolve in ways we don't yet comprehend? Could there be errors in our understanding of cosmic timescales? Or is there an entirely new model of the universe waiting to be uncovered? Michio Kaku, with his background in both classical and quantum physics, is uniquely positioned to interpret these findings. His willingness to engage with controversial ideas reflects the essence of scientific inquiry, to explore the unknown and challenge established norms. He emphasizes that scientific theories, no matter how cherished, are only as strong as the evidence supporting them. If new discoveries contradict the old models, it is the responsibility of the scientific community to investigate further and refine its understanding. As Kaku himself noted, the experimentalists play a crucial role in keeping theorists grounded. The James Webb Space Telescope, as a cutting-edge instrument, is a testament to humanity's ability to push the boundaries of observation. Its findings remind us that the universe is a vast and mysterious place, full of surprises that challenge our imagination and intellect. In the coming years, as more data is gathered and analyzed, we may find answers to the questions raised by these 6 universe breakers. Will they redefine our understanding of the cosmos, or will they reveal an even greater mystery? Whatever the outcome, one thing is certain: discoveries like these will continue to fuel humanity's curiosity and drive to uncover the truth about our place in the universe. To acknowledge awkward bits of insight and to comprehend that hypotheses are not outright bits of insight until they are thoroughly tried or affirmed by exact perception, the possibility of the Big Bang emerged from the acknowledgement that galaxies are creating some distance from one another, and this distance is proportional to their separation from Earth. This perception, known as Hubble's law, suggested that the universe was expanding. For quite some time, elements such as cosmic background radiation, the redshift of light from distant galaxies, and other cosmological structures seem to support this hypothesis. However, it is essential to remember that in the past, People who believed that the Earth was flat and that the Sun revolved around it also had physical evidence for their assumptions until coincidences or technological advancements provided a clearer and more accurate picture. Right now, we are witnessing a similar situation. Scientists expected the new James Webb Space Telescope, JWST, to confirm assumptions related to the Big Bang Theory. Instead, they discovered 6 galaxies that appeared to be impossible. This reminds us that science is continually evolving, and researchers must remain open to new discoveries and re-evaluate existing theories based on the available evidence. The surprising finding challenged the current understanding and prompted a reassessment of long-standing cosmological theories. Scientists use redshift as a tool to determine certain quantities in the study of the universe. Redshift, also known as the Doppler effect, refers to the change in the color of light as the light sources and the observer move relative to one another. To understand this, you can imagine standing still and observing a car coming toward you. As the car approaches, you hear the engine growing louder. However, once the car passes you and moves away, the engine sound changes. This happens because the frequency of the sound waves varies as the car moves. The same is true for light. When a light source, such as a distant star, moves toward us, the light we see shifts toward blue hues. On the other hand, when the light source moves away from us, the light shifts toward redder hues. This phenomenon is called redshift. Physicists have converted redshift values into velocities and distances for measurement in the study of the universe. However, it is crucial to note that small errors in these measurements could have significant effects. The measurement methods previously used are now under review, and it will be interesting to see the conclusions scientists arrive at regarding the latest findings about our universe. It is important to consider whether these findings are truly based on redshift errors, or if some researchers are simply denying the facts. This is a question that requires thorough investigation and careful review of the data and techniques used in the research. The current analysis and re-evaluation of measurement methods highlight the evolving nature of scientific inquiry. Many thanks for watching the video. As always, we remind you that you can post your questions in the comments box. If you liked Michio Kaku's analysis video, don't forget to hit the like button, share it so it reaches more people, and subscribe to the channel so you don't miss more content like this. Thank you for watching and see you in the next one. This call to action encourages viewers to engage with the content, fostering a community of curious minds eager to explore and understand the latest scientific discoveries. The study of our universe, with its vast expanse and intricate celestial structures, continues to captivate and challenge scientists across the globe. From early theories of the universe to the latest discoveries made possible by cutting-edge technology, each discovery reshapes our understanding of the cosmos and pushes the boundaries of human knowledge. One of the most profound and enduring questions in cosmology revolves around the origin and evolution of galaxies, cosmic cities of stars, gas, dust, and dark matter bound together by gravity. Understanding how galaxies form and evolve is crucial not only for unraveling the mysteries of our universe but also for confirming or challenging existing theories, such as the Big Bang Theory. The Big Bang Theory, proposed nearly a century ago, posits that the universe began from a single, infinitely dense point and has been expanding ever since. This idea emerged from observations of the universe's expansion and the cosmic microwave background radiation, considered the remnants of the early universe's intense heat and light. However, recent discoveries, particularly those made by the James Webb Space Telescope, JWST, have challenged some fundamental assumptions underlying the Big Bang Theory. The JWST, with its unparalleled sensitivity and resolution, has detected galaxies that defy conventional understanding. These galaxies, dating back to within a few 100 million years of the Big Bang, are unexpectedly massive and luminous, suggesting a more dynamic early universe than previously imagined. The implications of these findings are profound. They raise questions about the timeline and mechanisms of galaxy formation, prompting scientists to rethink existing models. For example, the discovery of galaxies that are already so developed shortly after the Big Bang challenges the notion that galaxy formation was a slow and gradual process occurring over billions of years. Moreover, JWST observations have highlighted the complexity of cosmic evolution. It is now evident that galaxies can grow rapidly and exhibit significant star formation activity early in their histories. These insights compel astrophysicists to revise their theories on how stars, gas, and dark matter interacted in the universe's infancy to form the first galaxies. Beyond reshaping our understanding of galaxies, these discoveries underscore the critical role of technological advancements in advancing astrophysical research. The JWST, with its infrared capabilities, allows scientists to look deeper into space and further back in time than ever before. By studying the light emitted by distant galaxies, cosmologists can reconstruct their histories and uncover clues about the conditions that prevailed during the universe's early stages. The concept of redshift, a key tool in cosmological research, plays a crucial role in these investigations. Redshift refers to the phenomenon where light from distant celestial objects shifts toward longer wavelengths as they move away from us. This effect, known as cosmological redshift, provides valuable information about an object's distance and velocity relative to Earth. Through meticulous analysis of redshift data, scientists can deduce the size, age, and evolutionary stage of galaxies observed by telescopes like the JWST. However, interpreting redshift measurements requires precise calibration and an understanding of potential sources of error, such as gravitational lensing and instrumental limitations. In addition to studying individual galaxies, cosmologists are also investigating larger cosmic structures, such as galaxy clusters and superclusters. These vast assemblies of galaxies are bound together by gravity and offer insights into the distribution of matter on cosmic scales. By mapping the spatial arrangement of galaxies and measuring their velocities, researchers can trace the cosmic web, a filamentous structure that spans across the universe and defines the large-scale architecture of galaxies. The cosmic microwave background, CMB, radiation represents another invaluable source of information for cosmologists. Discovered accidentally in 1964, the CMB is the faint glow of radiation left over from the Big Bang itself. As the universe expanded and cooled, the intense heat of the early universe diminished to a few degrees above absolute zero, leaving behind this pervasive background radiation. Detailed measurements of the CMB's temperature fluctuations provide a snapshot of the universe's infancy, revealing primordial density variations that eventually gave rise to the galaxies and cosmic structures observed today. These detailed measurements of the CMB, combined with the groundbreaking observations of the JWST, emphasize the importance of collaboration between theoretical models and advanced technology. Together, they enable scientists to explore the origins, structure, and evolution of the cosmos. As researchers probe deeper into the mysteries of the universe, they are often met with findings that challenge established theories and assumptions. Such discoveries highlight the dynamic nature of science, where evidence-based inquiry drives continuous refinement and progress. The unexpected discoveries of massive luminous galaxies in the early universe serve as a reminder that our understanding of cosmic history remains incomplete. The James Webb Space Telescope has opened new doors in cosmology, allowing astronomers to observe phenomena that were previously inaccessible. This leap in capability forces the scientific community to question long-standing ideas and adapt to new insights. While the Big Bang theory remains a cornerstone of modern cosmology, its details, particularly those regarding galaxy formation and evolution, are being revisited and refined in light of these recent observations. Looking forward, future advancements in telescope technology, computational modeling, and data analysis are expected to shed even more light on the mysteries of the cosmos. Tools such as gravitational wave detectors and next-generation observatories will complement the work of the JWST, enabling scientists to delve deeper into phenomena such as black holes, dark matter, and dark energy. These efforts will not only expand our knowledge of the universe but also help address some of the most profound questions in physics and astronomy. The exploration of space remains one of humanity's most inspiring pursuits, offering glimpses into the origins of existence and our place in the cosmos. The discoveries of today will undoubtedly pave the way for the scientific revolutions of tomorrow, as each new piece of evidence brings us closer to a deeper understanding of the universe's vast and complex tapestry.